So there was an ancient Greek philosopher called Zeno, and he realized something that perhaps first time you see it makes a lot of sense, but at the same time obviously can't be true, and that's called Zeno's paradox. And this is what Zeno argued. He said, imagine you've got a hare, here's my hare, and a tortoise. Obviously, you'll know the famous story about the hare and the tortoise winning the race. This is a slightly different variation, but will also involve the tortoise always being ahead of the hare. Because what Zeno said is, okay, the rabbit runs faster than the tortoise. He accepted that the rabbit moves faster. And he said, so imagine the rabbit runs and catches up to where the tortoise was. Let's put a little marker on my tortoise. You can see. So we'll call that there. We'll put a little marker on the rabbit as well, so that we're not running the risk of being too imprecise. So the rabbit runs and catches up to where the tortoise was. But obviously, in that time, the tortoise has moved. And the tortoise doesn't move as much as the rabbit, but it's definitely moved. So by the time the rabbit gets to where the tortoise was, the tortoise has moved on. But the rabbit's still running and still running faster. And he catches up to where the tortoise was again. Obviously now the tortoise has moved. And what Zeno said is that every time the rabbit catches up to where the tortoise was, oh, I've ungrouped it. Every time he catches up to where the tortoise was, the tortoise will have moved just a little bit again. It gets smaller and smaller every time, but it's always, the tortoise has always moved by the time the rabbit gets there, or the hare gets there. And therefore Zeno said the rabbit can never overtake the tortoise, because whenever the rabbit catches up to where the tortoise was, the tortoise has moved again. And yet, if we were to watch it, if I was to put a rabbit down and a tortoise down and let the rabbit try and catch up to the tortoise, obviously it would, and obviously it would overtake it. And yet, the argument that Zeno presents with this rabbit catching up to the tortoise every time, and the tortoise will always be a little bit ahead. And that's related to what we're going to talk about today, which is geometric series. And we'll come back to the tortoise and the hare at the end. So we've talked about what a geometric series was. We have a geometric series that went to 6, 18, whatever 3/18s are, 30, 24, 54, 162, and so on. So we've got a geometric series, and we want to be able to add them up. I want to do a similar thing to what we did with the arithmetic progression. I want to know what the total of that all the way up to, I don't know, all the way up to a big number. Let's say the 10th term. And we can do something similar to what we did, but not quite the same, because in the arithmetic progression I could just flip it around and I would get my pairings, and I would be able to pair them up and they'd all be exactly the same. That's not quite how it works with the geometric progression. So my geometric progression in general is going to go like this. U1, that's the first term. The next term is U1R. Second term, the third term is R squared. And then the last term, our nth term, is U1R to the n minus 1. And what I want to be able to do in some sense, is have another variation of that and eliminate basically all of it and just be left with a few little bits. So what I'm going to do is I'm going to multiply it by r. If I multiply it by r, I get this. Well, u1 becomes u1r. u1r becomes u1r squared. There's a term here that's going to become u1 r to the n minus 1. And then the last term will be this times r. So I've got r to the n minus 1 and multiply that by r again. That gets rid of the minus 1, right? So these are all being multiplied by r. Multiply by r, and we get u1 r to the n. u1 r to the n. Now I'm going to ask you to pause it there and see if you can figure out algebraically how to take these two quantities and combine them. And a bit of rearranging, you'll have to factorize something if you do it correctly. You should be able to get a formula for Sn for a geometric series. Okay, what I hope you realized is that I can subtract these two things, one minus the other. Rsn minus Sn. And what will happen is that nearly all the terms on this side will cancel, and you're just left with u1 r to the n minus u1. Now on both sides I can factorize that expression, those two expressions. On the left I can take Sn out as a factor, and I'll be left with r minus 1. And on the right I can take u1 out as a factor, and I'll be left with r to the n minus 1. Now, don't fall into the trap in thinking that you can cancel something. These two factors one is not a factor of the other. So I'm not going to be able to cancel this n or anything, but I can obviously write an expression for Sn just by dividing both sides by r minus 1, and I get u1 r to the n minus 1 divided by r minus 1. So let's say I had my geometric sequence here, and I wanted to know what they all add up to the 10th term. Well, I know that u1 is 2, r is 3, it's being multiplied by 3 every time, and n is 10. I'm looking for the sum of the 10 terms. Then I just have to evaluate for S10 2 times r, which is 3 to the power of 10 minus 1, all divided by 2. Oops, 3 minus 1 is 2. So that's a 2 on the top, that's a 2 on the bottom. Just left with, in this case, 3 to the 10 minus 1, which is going to be a big number. And I don't have my calculator at hand, but you can work out what that is. It's left as an exercise. So that's how we can calculate the sum of a geometric series. I imagine you're wondering, what's that got to do with hares and tortoises? I'm getting there. one of the really neat things, one of the kind of unintuitive things about geometric series is that, okay, that all makes sense what we've just done there. We've added up 10 terms and we've got a number in the thousands, 3 to the 10 minus 1. If the numbers are small enough, then we can add them all up. Not just the first 10, not just the first 100, not just the first 1,000, but every single term in that sequence off to infinity. An infinite number of terms are going to give us a finite solution. So it doesn't always work. There are some conditions. I'll give you an example where it does work. So let's say I want to add 1 plus a half plus a quarter plus an eighth plus a 16th and so on. And I'm going to add all the terms up, not just the first 10 or first 100 or first million, but every single term. So this is a geometric sequence. It's a geometric sequence where the first term is 1, the ratio is a half. If you do that on your calculator, you'll see that it gets closer and closer to a single number. We can't add them all up physically. We can't tap every single number in our calculator. But as they get smaller and smaller and smaller, you'll notice that it should get closer and closer to a single number. And it should make sense what that number is as well. So let's imagine that you've got, well, there's an old joke. A mathematician walks into a bar and he orders a pint. There's his pint. And then his mathematician friend walks into a bar and he orders half a pint. Oops, his beer's black apparently. He's got Guinness. It's not important. So they're both drinking Guinness, let's say. It's not like void. Guinness is the only beer available at this bar. Now, there aren't just two mathematicians. There's an infinite number of mathematicians. An infinite number of mathematicians walk into a bar, and the first one orders a pint. And the second one orders half a pint. The next one orders a quarter of a pint. I didn't say it was a funny joke. It's funny if you're a mathematician. The next guy orders an eighth of a pint. Next guy orders a 16th of a pint. And that's not how the joke goes. The joke just goes, infinite number of mathematicians walk into a bar. First one walks in, orders a pint. Next one says, I'll have half of what he's having. Next one says, I'll have half of what he's having. The barman says, know your limits. That's a pun on limits, and pours 2 pints. So why does he say know your limits? Because what's happening here is that we're getting closer and closer to a full pint. Each subsequent mathematician is adding a smaller and smaller amount, starting with a half, and then a quarter, and then an eighth, and then a 16th, and then a 32nd, and then a 64th, and you can see that that's never going to get to 2. It's never going to get to a second full pint. But it's going to get closer and closer and closer to 2 full pints. So we call that a limit in mathematics. We say the limit, as n tends to infinity, so as n gets closer and closer to infinitely big, of 1 plus a half plus a quarter plus 1 over 2 to the n, the limit of that is 2. So how could we can sort of see that in a sort of the diagram hopefully helps. Maybe adding it up on the calculator helps. How can we work that out for any number, not just 1, starting with a whole 1 and having a ratio of a half every time? Well, it works like this. The geometric formula that we've seen for the sum of a geometric sequence is given by u1 r to the n minus 1 over r minus 1. So what we're going to say is, well, what happens in the limit as n gets really big? As n gets really big, what is the limit of this formula? Sorry, always doing that. N minus 1 over r minus 1. Well, there's only, in that formula, there's only one occurrence at n. So we're only really interested in what happens to r to the n as n gets really big. So let's suppose r was some number, let's say 3. Then what would happen to r to the n as n tended to infinity? As n got really big, what would happen to r to the n? Well, 3 squared is 9, 3 to the 3 is 27, to the 4 it's 81, to the 5 it's 243. It gets big really quickly. So if r is 3, then this is just going to explode. So if one mathematician walked in and ordered 1 pint, and the next guy ordered 3, and the next guy ordered 9, there wouldn't be enough beer in the barrels. There'd be an infinite amount of beer required. But that doesn't always happen. This is the nice thing. What if r was a third? If r was a third, then what would happen to r to the n as n got really big? Well, if you start with a third, and then it'd be a 9th, and then it would be a 27th, and then it would be an 81th, and then it'd be a 243rd, and that's pretty small, a 243rd. So what would happen as n got off to infinity is this, a third to the power of n would get closer and closer and closer to 0. So in the limit, we'd say that becomes 0. So going back to our limit, what happens as n gets really big to this formula? Well, as long as r is not bigger than 1 and not smaller than minus 1, so as long as r is between minus 1 and 1, so it's a fraction, because we know that when we multiply a number that's smaller than 1 but bigger than minus 1 by itself, it gets smaller. If you multiply 1 by itself, it stays the same size, and if you multiply something bigger than 1, it gets bigger and bigger and bigger and bigger. But anything between those two values, between 1 and minus 1, every time you multiply it, it gets smaller. So a third, a 9th, a 27th, an 81th, a 243rd, getting smaller every time. And that's true for every number between 1 and minus 1. So this formula, this infinite formula, that we're going to call S infinity, it's only true if r is between 1 and minus 1. And what happens? Well, what happens is that this bit goes to 0. So that just vanishes. And we get u1 times minus 1 over r minus 1. Because this bit is gone. Now that's a little bit ugly looking because that minus in the top. So I'm going to multiply the top and the bottom by -1. Get rid of that negative. So negative times negative makes positive. So I've got positive u1 on the top and 1 minus r on the bottom. S infinity, and that's the sum, the infinite sum of a geometric sequence. So let's suppose, let's go back to our pints of Guinness example. In our pints of Guinness example, the first term was 1. And each time, each mathematician was ordering half of what came before. Which means that the infinite sum, which the barman calculated in his head, and when he said, know your limits, that was his clever little pun on on knowing your limits mathematically and also knowing your limits on how much you can drink. S infinity will be 1 over 1 minus a half. Just substituting these values into that formula. 1 over 1 minus a half, which is 1 over a half, which is, how many halves go into 1? 2. And it would work with, so here's a nice little proof of a fact that is not always obvious, that 0.9 recurring is 1. So let's say I've got this sequence, 0.9 recurring is obviously equal to 0.9 plus 0.09 plus 0.009 and so on, an infinite number of times, right? If I add 0.9, 0.09, 0.009, an infinite number of times, then what will I get? Well, I'm going to leave this as an exercise, and this is what I'd like you to do before you come to the lesson. In this sequence, I'd like you to identify what U1 is. I'd like you to identify what R is. And hence, I would like you to calculate S infinity. And show that, you should, if you do it correctly, you should get the answer 1. Thereby proving that 0.9 recurring is equal to 1. I will see you next lesson.